Hi guys, Mrs. Rona here. We are on pages 26, 27, and 28 of our packet. We're going to go through the notes for target number 3. If at any time you need to pause this video to write some stuff down, please feel free to do so. You can always rewatch any parts that I go too fast. But this is target 3. It says I can analyze collisions using the law of conservation of momentum. So terms you want to know are law of conservation of momentum and recoil is another thing we're going to introduce. So we do have all of these equations for this unit. They're on the bottom of page 26. The first 3 should look familiar. Those are from target 1. The next 3, the long ones with mass and velocity in them, those are the 3 we're going to look at this unit, or this target 3. So 1, 2, 3, they look similar, they're slightly different, and we'll talk about how you decide which one to use. All right, conservation of momentum. So top of page 26, I've underlined the things that fill in the blank. So when two objects interact, Newton's third law tells us that they exert equal forces on each other. So here's an example of two objects colliding. They exert equal forces on each other, but they are opposite in direction. So force 1 would be equal to negative force 2. The time of contact is also the same for both. So however long this red object is in contact with this gray object, those times are equal. Because of this, we know that the impulse the objects exert on each other will also be equal in magnitude and opposite in direction. So they apply the same force for the same amount of time, so their impulses, force times time, is equal to each other, just opposite in the direction. This means that when we add those vectors together, we get a net impulse of 0. So ft1 plus negative ft2, since they're equal but opposite in direction, they kind of cancel each other out to 0. So no net impulse means no net change in momentum, because impulse always equals change in momentum. So even though the velocity of each of these balls is going to change after the collision, their momentum before and after is the same. And this is what you should have seen from the activity yesterday, that if they had a total of 2 kilograms times meters per second before, they'd have afterward a total of 2 kilograms times meters per second. This is the law of conservation of momentum. In the absence of an external force, the momentum of a system remains unchanged. Momentum lost by one object is gained by another. The total amount of momentum will stay constant. So if we wrote this in equation form, the P initial, momentum initial, is equal to P final. So at this point, you should have all of those blanks at the top of page 26 filled in. If you need to rewind and replay, go ahead and do that, but we're going to move on. All right, so there are 3 scenarios where momentum is conserved that are a little bit different. So we're going to look at each of those. The first one is when objects do not stick together. So there's a collision and the objects do not end up together afterwards. So the background picture here are kids in bumper cars. Bumper cars bump off of each other, and so they are not sticking together. So example 1 is 2 rubber balls are rolling towards each other. The gray ball is traveling to the right with a velocity of 3 meters per second, and the white ball is traveling to the left with a velocity of negative 7 meters per second. After they collide, the gray ball has a velocity of negative 2 to the left. What is the final velocity of the white ball? Clearly, these objects do not stick together, and so the equation we want to use, it always starts from the same root equation, that the momentum initially is going to equal the momentum at the end. But this one, this is the first equation on the bottom of page 26, and this is the equation we use when objects don't stick together. I can tell that because this mass and this mass are separate. There's a plus sign between them saying they are not together. And then after the collision, so after the equal sign, those are not together then either. So the longest equation at the bottom of page 26, actually the middle one, has the masses separate to begin with and separate at the end. And that should mirror your picture. The masses are separate to begin with and separate at the end. So we're going to use that equation to calculate the final velocity of the ball. And I've changed these to kilograms because I don't want to convert to grams. So you can do that on your paper too. Let's go ahead and plug in those numbers. So mass 1, we can say is the mass of the gray ball, so 8 kilograms, times its initial velocity is 3 meters per second. So I'm just combining for the beginning of this. Mass 2 would be the white ball, so 5 kilograms, times its initial velocity, which is -7. Hopefully you're copying this down on the bottom of page 26. After the collision, we said M1 was the gray ball, so it still has a mass of 8, and its final velocity is -2. And the final mass of the white ball is 5, and its final velocity is, we don't know, that's a question mark. Okay, so I've plugged in all of my variables. Now I can go ahead and solve this out. So 8 times 3 is 24, plus 5 times 7 is -35, equals 8 times -2 is -16, plus 5 times, I'm going to call that V final, because we're looking for the velocity there. So I can keep going. 24 plus -35 is -11, equals -16 plus 5 times the final velocity. I'm going to add 16 to both sides. So I'm going to get 5 equals 5 times the final velocity. Divide both sides by 5, and you would get the final velocity of the white ball is 1 meter per second. Okay, so I'm using the calculation. Now that's not the only way that I can solve these problems. I can also solve them using a chart. So let's try another example on page 27 using a chart. Again, I know I'm moving fast, so feel free to pause and replay if you need to. So on page 27, the example is a 4-kilogram bowling ball heads towards a stationary pin at 5 meters per second. Right after being struck, the pin travels to the right at 3.2 meters per second, and the bowling ball slows to 4.5 meters per second. What is the mass of the pin? So our picture, we've got the ball moving to the right, the pin not moving. After they collide, the ball slows down a bit, the pin goes flying to the right. And we're going to try this one making a before and after table. On the quiz, you'll have the option to either use the equations or use the chart. And so the charts will be given to you, the equations will be given to you. You don't have to do both. You can do whichever one works best for you. So here's the chart. So let's plug in some numbers. So the ball's mass is 4 kilograms, and the chart's split into before and after. So its initial velocity is 5. And P, it asks you to actually solve for the momentum. So momentum's mass times velocity. So this would be 20, 4 times 5. The pin before, we don't know its mass. Its initial velocity is 0. It's at rest. And so anything, the mass times 0 is going to be 0. The pin is at rest. It doesn't have any momentum. Now what we want to do is solve for the total momentum before. So we would just add these two together and get 20. Now after the collision, the ball has still has a mass of 4, and it's moving at 4.5 meters per second. So to find the momentum, we do 4 times 4.5, and you get 18. The mass of the bowling pin, we still don't know, but its final velocity is 3.2. And so I don't know its final momentum. However, momentum's conserved. That's what this whole target's about. So the total momentum before has to equal the total momentum after. So we can plug in a 20 here for the final momentum of both the ball and the pin. So if this is 20 and this is 20, then we can solve for what that missing momentum was here, because 18 plus this has to equal 20. So this is going to be 2. So now that I know that, I can work backwards to find the mass of the bowling pin. So what I would do is I could say P equals mv. Turn off my caps lock. The final momentum is 2, is equal to the mass, that's my unknown, times its velocity, 3.2. So if I divide 2 divided by 3.2, I can say that the mass is equal to 0.625 kilograms. And so I've solved for that mass, and I can plug that into my chart. So using the chart is another way you can solve these problems. Let's fill this in because we found that. So again, the way the chart works, you find the total momentum before, set it to the total momentum after, and then work backwards to find whatever variable you're looking for. All right, so that's the first scenario when objects bounce off of each other. The second scenario is when objects stick together. So this would be like a football player, or playing football is a good example. When you make a tackle, you try and wrap the guy up and take him down. And so the objects become one object at the end. So if we look at the equation, we start with the same base equation. Momentum before is equal to momentum after. But now we know that the objects start separate and they end as one. So we can treat it as if the mass at the end is just one object. So this is the equation on the bottom of page 26. This is or 27 we're on now. This is all the way on the left, bottom left equation. The masses start off separate, and at the end they become one object with one final velocity. So example 3 is a train car with a mass of 500 kilograms is traveling to the right with a velocity of 7.5 meters per second before colliding and coupling itself, meaning it's going to stick together, to a 600 kilogram stationary train car. At what velocity will the two attached cars move after colliding? So if you look at the picture, you've got 500 kilograms moving to the right at 7.5 meters per second, 600 kilograms at rest. Then they couple together. So you've got a 500 kilogram and a 600 kilogram moving together at the end, and the final velocity is what we're looking for. So we're going to use that equation. Actually, not this one. We're going to use the one right up here where we have them combining into one object at the end. So go ahead and copy that equation down, because that's the one we're going to start with. Oops. And I'm going to go ahead and start plugging in numbers. So M1 we're going to call the yellow car. So it has an initial mass of 500 and a velocity of 7.5. M2 is going to be that gray car, which is 600 kilograms. And it's not moving, so its initial velocity is 0. Afterward, they combine together, so I can add their masses together. So 500 plus 600. Times velocity final is my unknown. That's what I'm looking for here. So if I want to go ahead and solve that, I can do 500 times 7.5 is equal to 3,750, plus 600 times 0 is 0, equals 1,100, 500 plus 600 times V final. So now I'm just going to divide both sides by 1,100. And I get that 3.41 meters per second is equal to V final. So these cars will stick together and move to the right at a velocity of 3.41 meters per second. All right, guys, we have one last type of problem, and that is recoil. So recoil is when objects start together and they start at rest and they go out from each other. So one goes forward, one goes backward. So firing a gun is an example. So here is an example of one. This is on page 28. A cannon is with a mass of 500, fires a cannonball with a mass of 10 kilograms at a velocity of 30 meters per second. What is the recoil experienced by the cannon? So we are looking for how fast does the cannon get pushed backwards because the ball goes forward. So this equation, the masses start together and end separate. So recoil, you're looking for masses together at the beginning, separate at the end. So let's try with a table. The initial mass of both of them together is going to be 510 kilograms, and they're not moving. They have an initial velocity of 0, and that's another kind of hint that it's a recoil problem. So their total initial momentum is 0. They're at rest. After the cannonball is fired, the cannon has a mass of 500, the ball has a mass of 10. We don't know the final velocity of the cannon. The ball has a velocity of 30, and so we're looking for their final momentum. So we know that total momentum before is equal to total momentum after, so this has to still equal 0. 10 times 30 is 300, so we know that this one is going to be negative 300, right? These two need to add up to 0. And so using P equals mv, if the final momentum is negative 300 and the mass of the cannon's 500, we can solve for its final velocity. So divide both sides by 500, and you get negative 0.6 meters per second. All right, thanks for watching. Go back and watch anything you missed, and you can get started on your homework. Bye.